Then full screen.
Cool.
Okay. We start.
Nice. Okay, so right, so we've done the sort of general theory, and then some sort of archetypal examples, and now we're gonna deform the examples a bit and try to solve some more challenging problems, or at least see what sort of modifications of processes we can accommodate. So as I said, in the previous examples, the natural metric was sufficient. You didn't have to think about it too hard in some sense. What we'll see is that in the absence of things like uniform convexity or uniform minorization, etc., we have to work a bit harder. A general trend, which people will be familiar with from various examples, I think, is often you will have situations where in the tails of the distribution, things are working very nicely. You have a lot of regularity and everything is pushing you into the center of the space. But in the middle of the space, things can be a bit more challenging. The sort of archetypal thing to have in mind is when you have strongly convex tails but non-convex middles, something like this. And we want to find some way of sort of combining these regimes gracefully without paying exponential intervention costs also, which sometimes you can't avoid. Okay, so what I'm going to present here is a pretty general result related to what's in the Debrushian stuff I talked about before. And the idea is the following. So in many cases, you will not have contraction in the metric that you would like to, but you will be able to write down a few different metrics where you sort of jointly contract with respect to a bit of each of them. In one part of the state space, your first metric will behave well, and the other part, the other one will, and they sort of compensate for one another in a suitable way. And so this result is a way of stitching that together into a metric which does contract. And I'll try to explain that. So let DI be a collection of metrics, and suppose that there is a matrix A with non-negative entries such that for each x and y there's a coupling such that the following holds. So the one-step expectation of the ith metric can be bounded above by a linear combination of all of the other metrics. Okay, so in principle, for a big A, this could be almost a trivial bound, right? But we're going to hope that we can get Aij to be sort of small for many of the elements. And so what's true? So you construct these estimates for all of the I, and then you look at your matrix A. And what's true is that if you have a spectral radius which is less than 1, so the operator norm might be bigger than 1, but the largest eigenvalue of A, which will be unique, that statement doesn't actually mean anything, but if the largest eigenvalue is strictly less than 1, you can find a vector with non-negative entries such that P has positive curvature with respect to a weighted combination of these things. Okay? And so this is a sort of simple proof if you know a few facts about things. So basically, there's a result called the Perron-Frobenius theorem, which is a theorem about finite matrices with non-negative entries. Actually, there's more general versions, but at least say that. So for finite matrices with non-negative entries, it's known that they have a largest eigenvalue, and to that largest eigenvalue, there is an associated eigenvector, which has all positive entries. Okay, so we mostly use that for Markov chains, right? Because the matrix in a Markov transition is has this form, and so the eigenvector is the invariant measure for us. But here, there's no Markov chain. It's just sort of an abstract matrix. And so what happens is we're essentially saying, if I think of, if I stack all of these DIs into a vector, right? I'm saying the expectation of this vector after one step is majorized by A applied to that vector at the previous step. Right? So you have something that's like, so the expectation of d n plus 1, given all the information up to time n, is partially ordered by A times dn. Okay? And so we have a sort of linear inequality. And so if we iterate this, you sort of believe that if A has eigenvalues less than 1, you will sort of decay eventually. Right? And so the way we use Perron-Frobenius is just to say, actually, I take the inner product of V with this distance vector. I get something which is a linear combination of distances and with positive coefficients. So it's again a distance. And so I have that this thing will contract at this rate here, because you're exactly extracting the eigenvalue of A on the left. Say. Okay, and so this is something nice to think about later if you're interested. But essentially it says if you're able to establish estimates of this form, sort of compensated contractivity, if you like, or weak contractivity, something like this, you have a direct route to getting contractivity in another metric. Okay, and so that's sort of a technique we'll use in the remainder of the lecture. You know, I hadn't seen this written down, but I'd seen people use the same idea numerous times. And also when I was sort of reading various papers, people don't sharpen the estimates so much because you just want to show that you have a spectral gap. But actually this gives you a way of getting sort of the sharpest estimate that's available to you, which is...
Doesn't contractivity sort of have a reducibility condition, or does that not matter here?
It doesn't matter here. All I need is to extract the leading eigenvector, which definitely exists.
Okay, so it doesn't matter, you don't care about uniqueness or that kind of thing?
No, because I just want the estimate. And so actually a quick comment is that this thing with diversion earlier was sort of a version of this, right? Except that our DIs weren't metrics, but semi-metrics. They were the sort of ith Lipschitz constants, right? But okay, so the program from here onwards is to try to treat some interesting cases of Markov chains where obtaining contraction with a standard metric is not an option, but if we use this sort of, you know, I would call it a multi-scale contraction or a hybrid contraction or something like this, is feasible. In all the examples we do, 2 will be enough. It will almost always be bulk behavior, tail behavior. Okay? But in principle, the general thing might be useful. I included this formulation because of the diversion construction. Okay, there's one construction which arguably is taking n equals infinity in a certain sense, but it's a bit hand-wavy for me to say that. But I'll sort of point that out. And yeah, just notationally, you know, you don't need to remember this, but I think I've tried to keep it consistent so that D1 is the metric that contracts well when you're in the center of the space, and D2 is the one for the tails. Okay. Yeah, so these examples are more involved technically, and so I haven't included the details to the same extent, but these are from research papers from the last 5 or 10 years where I wanted to understand the result, and I have PDFs on my computer where I've spent 5 pages, you know, optimizing the constants and figuring out what's going on. And so if you care about the examples, I will talk to you. Okay. But here is to sort of convey some intuition for why you might stitch things together in this way. Okay, so we're back to diffusions. Okay, this one, again, it's sort of not necessarily Langevin, but at least additive noise. That tends to make life much easier in almost every respect, I think. Okay, and so now we're going to assume what I would call a varying contractivity or a weak contractivity assumption, which says when you have 2 points that are at distance r from one another, the sort of contractivity between x and y at that distance is at least kappa of r. So when this kappa is positive, you have good contractivity. And when it's negative, you might have a bit of repulsion, okay? And so we will not assume that it's positive in particular. And so the standing assumption will basically be that once you get your 2 chains sufficiently far enough away from each other, they will contract. Okay, so it's like a strongly convex in the tails type assumption. And then in the center of the space, you kind of they have bounded repulsion, let's say. So when they're close together, they might really want to push apart, but not in a really singular way, let's say, like you might have in certain physical systems. Okay, and so you'll see this on things like distant contractivity, strongly convex in the tails, etc. So this is interesting for things that are a bit multimodal, but it's somehow it's just a nice assumption where the proofs go through and you get a bit of intuition for things. It's not clear how many practical examples this holds for with very nice constants. In particular, you know, this in many cases you would expect this. Well, I'll get back to that later. Okay, so in this case, when you don't have global contractivity and you even have a bit of repulsion, you know that synchronous coupling will not work. At least, well, definitely not in the almost sure sense, because we know that when they get close enough, you know, that you are actually pushing them apart. But actually, you know, you can probably show in some cases that you can't even get it in the average sense. Okay, so we have to try something else. And so the idea, which I can just phrase as an ansatz at the moment, is instead of feeding them the same Brownian motion, you sort of try to gamble a little bit more, and you say, I look at the noise that I'm feeding to the 2 particles along the line between the 2 of them, right? The one where if I synchronize them both, I get quite a bit closer, but if I synchronize them in the opposite direction, then I get unlucky. So you're sort of chancing it a bit. Okay, and so this is a thing you can do. And one reason you might consider it would be if you wanted to, so if you consider the example of sort of 2 diffusions on the circle or the interval with periodic boundary conditions, it's known that this works. Okay, basically what happens is, you know, you get lucky often enough that you do actually collide in the end. Okay, so in the original metric, using reflection coupling will also not give you contraction. Still an error. It actually makes things worse. Okay, so what's happening is if you're measuring things in a convex function of the metric, adding these extra noises in the opposite directions makes things worse, and it's basically Jensen's inequality. And so that's a bit frustrating. But the other thing about Jensen's inequality is that you can play with it a bit, right? And so if we instead take a concave function of the metric, which I sort of hinted at in the first section, things go the other way, right? And this idea of chancing it to try and get things to contract much better actually works in your favor. Okay? And so, as I said before, if you take a function which is 0 at 0, increasing in concave, so you know, when I'm in my notes, I really just write f is blah, because that's always what I'm imagining, right? So composing that with a metric gives you a metric. And so the fact that it's concave means that this sort of short-range repulsion that you may be dealing with will eventually lose out to the reflection in the diffusion somehow. That even though this could dominate if you had a synchronous coupling, it will eventually lose out with the reflection coupling because there's enough drift back towards 0 on the distances. So this is related to the comments I made at the start about reducing to a one-dimensional process. What we're essentially going to do is try to study the distance, the Euclidean distance between xt and yt, and show that it satisfies a stochastic differential inequality, basically. So I will omit the details, but if you've done a bit of stochastic calculus, or if you look it up on Wikipedia, you can more or less reproduce these calculations. So if I have my chains as xt and yt, and I do this reflection coupling, which I've been a bit vague about here, but again, it's just this idea that you look at the component of the noise along the distance, the displacement x minus y, you sort of antithetically couple them. Then you can, for any suitable function f, you can get this differential inequality. This might actually, oh no, this is an inequality. Okay. So that the rate at which this modified distance is changing is a martingale term, which means we can ignore it, basically, so that's mean 0 on average, minus this plus this. Okay. And so we'll see, since f prime is positive, because we're dealing with an increasing function, when kappa is positive, this is drifting us back down towards 0, which is good. And if we choose f to be concave, this term is negative. Again, we get some push towards 0. Okay? And so in principle, you could try to study this and say, how long does it take for me to hit 0? But actually, we'll be content to show that this thing contracts exponentially in expectation. So we don't care if we hit 0, we just want to have small expectation. It's completely fine for our purposes. Okay. And so if we want to show exponential contractivity at rate c, we can sort of say, as I was saying, ignore the martingale term and show that this drift is bounded above by a constant times the object that we care about. Then we say Grommel's inequality 3 times. The theorem is proved. Okay. And so the tricky work from here is to explicitly construct an f of this form for a suitable c. Okay. And this is hard to do in words. But essentially, what we know is that in the tails, we've made an assumption that we have strong convexity there, right? Which means that in the tails, we don't need to change the metric so much because things are working well already. And so our function f will be asymptotically linear, basically. We don't mess around there. And in the center of the space, we will sort of try and do something like this to make it a bit more favorable. And actually, the construction is basically as follows. You try to solve this differential inequality with c equals 0. So you show actually there is a simple, pretty explicit metric where the dynamics are non-expansive on average. Even this is not obvious a priori, right? You have this repulsion in the center of the space. It could easily go wrong. So you get the solution with c equals 0, and you sort of use it to build an ansatz of what f should look like for c greater than 0, and then you solve the differential inequality approximately. And you sort of break up the interval on like, for small r, I should do one thing. For large r, I should do another thing, depending on whether this kappa is positive, negative, etc. Okay, and so this is work of Andreas Eberle, and it's sort of, I think, one of the most impressive results in using non-standard metrics and couplings to get new contractivity values. Because this really lets you handle cases where an almost sure contractivity is never happening. Right? There are sort of limitations to what you can accomplish with it in high dimension, but it's still, I think, a super nice result. And actually, many of the subsequent results that I'll talk about, Andreas was involved in to some extent or another. So he's thought very carefully about this stuff. I should say on a historical note, so this idea of working with a transformed metric and reflection coupling, that does precede Andreas's work, and it was sort of studied in the 90s by Chen and Wang. Again, sort of, they write their papers like they're talking about PDEs, but all the constructions are sort of Markov processes. They also have a habit which, whether you like it or not, they will almost always do things in the general case of manifolds. And so when you're reading the paper, you have to sort of digest, like, what does this actually mean in one dimension, so I can understand what's going on. But they're very clever and they've done very good maths. Okay, so that's the first one. So I said one of my examples is kind of like taking n equals infinity, and it's this one. So you're sort of stitching together all of the different scales at which particles can be far apart from one another and combining them in this concave way. I don't know a way of writing it explicitly as I have before, but I suspect probably this can be interpreted as some infinite dimensional matrix equation or something like this. And even without that, the construction is sound. Okay. So another example, which this is one where I really like the paper and it's super well motivated. So it's nice because it gets back to some notions which people in our area are particularly familiar with, right? So we're going to assume that our Markov chain has what I would call an inward drift condition, where you have some sort of nice coercive Lyapunov function v, where upon taking one step of the Markov chain from any state, the value of v shrinks in expectation by a constant factor up to a sort of fudge down here. Right. This is basically saying if we're in parts of the state space where v is big, we will exit them quickly and drift towards the parts of the state space where v is small. So that's a drift condition or a Foster-Lyapunov condition. And then secondarily, we assume that there is an R which is big enough such that when we look at the set where the Lyapunov function is smaller than R, we have what's called a minorization condition. Okay, and this, for me, one way of interpreting it is a small world thing. So once you enter the set C, any 2 points in that set can couple easily. Okay, it's like a local version of this Dublin condition I talked about in the previous section. Okay, I think it's reasonably well understood by now that you can make this condition hold with pretty good constants, and it's very difficult to make this one hold with good constants. But for qualitative results, it seemed to be pretty invaluable. Everyone kind of, and there are even sort of nice converse results that say if you have geometrically ergodic Markov chain, something like this has to hold. Okay? And so that's sort of one of the values of it. So the intuition is when you're in the tails, you drift inwards because of this, and the tails are really defined in terms of this v. And in the bulk of the distribution, you couple uniformly easily. And inside this set, everyone's friends with probability alpha. Right? And so you'll see this referred to as a Mine and Tweedy style condition because of Mine and Tweedy's book on Markov chains and stochastic stability. And they push this reasonably far. I should say a nice note is, so there's a work in, I want to say, the late 90s by Sean Mine and Peter Glynn, where they study the Poisson equation for Markov chains using these techniques. And with the benefit of hindsight, they're using sort of the curvature approach to get the estimates they do. That's what I like about it. Okay. And so the presentation I'll show next is basically borrowed from a paper of Heyer and Mattingly from 2007 or thereabouts, where they sort of show that if you have these conditions, you have contraction in a hybrid metric, which involves the discrete metric, and again, this weighted discrete metric I talked about before. And so this is quite neat, even if it's quantitatively not tremendous. So, right, D1 for the discrete metric, that makes sense, because in the center of the space, the discrete metric will contract well because of the Dublin condition, okay, because of this minorization. And in the tails, the V-weighted discrete metric will work well. So I should, so this is the one that's V of X plus V of Y when the 2 points are distinct. You can see that this should contract well in the tails, because in one step, you will go from V of X plus V of Y to PV of X plus PV of Y plus constants. So you're sort of shifting nicely. Okay, and so here you can do a case-by-case analysis, basically stratifying on whether X and Y are both in the center of the space, or at least one of them is not. Okay, and so you can show that the expected D1 between them, which is the probability that they're no longer equal to one another, you can bound it by 1 minus alpha if they're not equal to one another, and that's the term that comes from when they're both in the center of the space. And then you can only bound it from above by 1 when they're outside, right? When they're outside of the center of the space, there's no reason for them to couple. And you know that on that space, D2 is greater than R, And so you get this inequality. Again, we don't have to go through it carefully, but it's all elementary stuff. Similarly, if we want to look at how the D2 is contracting, so how is the Lyapunov function going down, right? We know that we have this 1 minus gamma from what I've written here. And then you pick up a factor of k for each of the points because of this. Okay, so PV of x plus PV of y is less than the sum of this at x and at y. And so you get dot plus dot. Okay, and so now we have a 2 by 2 matrix. If you want to get the best estimate on the contraction rate, write down this matrix and tell me what its biggest eigenvalue is. Then you can go home. And if you look at the conditions that we've put on on how big the radius has to be, then it will tell you fairly directly that this matrix has an eigenvalue less than 1. And so you just do the work. Okay, so this is super nice to me. We're basically saying, and people have sort of correctly said this to me, it's like it seems like the contractivity condition is very strong, right? Which is true. But also, if you have a geometrically ergodic Markov chain, then you can prove it with a drift and minorization proof, which means it's contractive. So it holds. So the only question is the constants. Okay. So does the logic sort of flow there, right? If it's convergent, it's provably convergent in this way, and that proof implies contractivity. And so one of my big open problems in this area is basically, what I believe is if you have a Markov chain which is exponentially convergent, that there will exist a metric for which it is contractive in that metric with the same rate. And that would be fantastic to know, right? It would say, all of these nice extra things I told you in the first section, you would get them for some metric. And so that would be very nice. But that is extremely far from being proven. There's sort of versions of it that exist, but they're not really usable, I would say. Okay.
What kind of versions would this be?
So there's something called a resistance metric, which Carl Sturm had worked on and a couple of other people. And it's sort of, you construct a metric using the Dirichlet form in a sort of slightly indirect way. And there's some statement like, if your chain is exponentially ergodic in discrete time, then the Poissonized version of it is contractive with respect to this resistance metric or something. But it's like, it's not very usable in the sense that this metric, you can define it, but it's not even obvious that it's finite between any 2 points, for example.
But they must prove it, no? Or...
Well, so for the result I said, I think they assume that it's finite, basically. So this is why I believe it should be possible somehow, but there seem to be technical obstacles and stuff like this. I had been curious about whether, say everything's in the reversible case, so you have a spectral gap, whether you can define a metric using the spectral decomposition somehow, which seems likely to be true, but not necessarily easy to prove. So we'll see. Okay, how am I on time? Running out. Let's see. Yeah, okay, I'll do this one quick. Be intuitive. Okay, so say we've got a Markov chain on a metric space which has finite diameter. This you can remove if you need to. And suppose there's a threshold R where if the two chains are at least a distance R from one another, they will contract at the rate 1 minus kappa in the ambient metric, right? And once they're within R of one another, you can make them meet exactly with probability alpha. Okay, so this is weaker than minorization, right? It's saying once the chains are close together, not once they're in the same part of the space, the center of the space. Sorry. Okay, so when you're far apart, the chains contract well in space, and when they're close in space, they can coalesce exactly with good probability. Okay, and so in this case, we can do another case-by-case analysis, saying the discrete metric, well, it goes down with a probability 1 minus alpha once they're close, and it's bounded above by 1 once they're far, so sort of the same analysis as before. Similarly, if we want to do the contraction of the ambient metric, we know that when they're far apart, it shrinks by 1 minus kappa, and when they're close together, they can't end up more than the diameter apart from one another, right? And so that's where these terms come from. It's a good thing to do in your own time, and it's not so taxing. And again, we just use the same contraction limit. And it turns out that this finite diameter condition makes it easier to present the result, but you can remove that fairly easily if your chains don't make very big moves. Okay? You basically need to say when they try to couple and fail, things don't go disastrously. And we know that in most algorithms that will be the case. Okay, I'll comment on this one briefly without touching on the proof. But this is back to the diffusion case, and it's one of the sort of weakest set of assumptions I know where you can get good bounds. So you assume that your process satisfies something like this condition from, okay, this minus sign shouldn't be there, and that's absolutely crucial, actually. So the assumption is just, it's what's called a one-sided Lipschitz condition, okay? And what we're saying is that if you're at X and Y, the two chains don't diverge too quickly, okay? But if you ignore that minus sign, I'm not assuming this kappa is ever negative. I'm not assuming you ever have any contraction. It's just bounded repulsion. Okay, and then the other condition is sort of a continuous time version of the Lyapunov drift. You know, this function v goes down on average except when it can't. Okay, so this is what I would call, you just have inward drift, the tails are nice, and bounded repulsion, things are not too crazy in the middle. I think very reasonable, actually. And so this is in a paper of Eberle, Guilan, and Zimmer. So Zimmer was a PhD student with Eberle, and Guilan is sort of also very good at this stuff. And so in this case, what they do is they construct a sort of modified Euclidean metric in the same way as Eberle did earlier, this sort of concave function of the metric. And then they use this sort of V discrete metric based on in the spirit of what we did here, right? And they find a blending of that, which is contracted using much the same argument. Okay? And again, they have to use a reflection coupling. So the idea is in the center of the space with the reflection coupling, eventually you will beat the repulsion with the reflection. Okay. And so, yeah, a lot more care is involved, but structurally it's the same proof, right? You construct one metric, construct another, and then you take a linear combination of the two. Okay. Some final examples, just, we can talk about these later if anyone cares. So this sort of discrete, weighted discrete stuff that follows from the Mine and Tweedy way of doing things. This has been applied in the last couple of years to studying sort of positive semigroups in the sense of Feynman-Katz semigroups with killing and stuff like this. And so it allows for some sort of robustification of what Pierre Delmoral has been doing in the past. So many of the basic results on SMC assume essentially contractivity in the discrete metric, which is arguably too strong. But reducing to these Lyapunov weighted metrics is much more reasonable, I think. And so they've got some very nice recent results on that, which I think is in AAP with Emma Horton and AJ Jazra. Some very interesting things on switched Markov processes and PDMPs. So things where you have a finite number of diffusions or ODEs you could be following the dynamics of. And at any given time, you can, at some Poisson rate, switch to another one. Right, and so here it's natural to use a sort of discrete Euclidean hybrid metric, where the discrete metric is saying, are we using the same vector field or are we using the same SDE? And the Euclidean metric is just on the spatial variable. And there's some sort of very interesting results on this in a paper of Chloe and Hira. They have some interesting counterexamples there as well, which I like to talk about. And finally, so using the modified Euclidean contractivity stuff that Eberle pioneered has been very useful for things like particle systems and McKean-Vlasov equations, and even proving things like uniform in time propagation of chaos. So there's a really terrific paper by Dermus, Eberle, Guilan, and Zimmer in Transaction of the AMS. It's like 10, 15 pages, and it's super nice. If you know how hard these results can be, to see them do it in 10 pages is just phenomenal stuff. And there's many other examples, which I was trying to catalog in the lecture notes. Okay, so just the closing thoughts, and then I'll rattle off some open problems, possibly. So many Markov chains have positive curvature in some metric, and knowing that a Markov chain has positive curvature in some metric tells you quite a lot about the convergence behavior of this chain, not just in terms of mixing times, but in terms of additional information. These insights are enabled by being able to think of Markov chains through optimal transport theory, even though many of the metrics I've worked with have not been what people are normally thinking about in this area. When working with nice Markov chains, establishing a positive curvature condition can be very clean. When you're doing things for the first time with the strongest assumptions, often it comes very easily and you get many things for free. When working with these tougher Markov chains, you have to be more careful. And honestly, I would say there's a bit of creativity involved in what people are doing. Some of these things I would not have thought of, right? But it's very rewarding and you get results which are sort of robust and interesting. Yeah, and sort of a call to arms would be many relevant Markov chains, good curvature estimates are not yet known. And there is much work to be done. So to say some of them. Okay. Find a legitimate statistical problem where you can apply the Debruchin estimates to a continuous system and get meaningful things out of it. I think this is possible, probably with spatial statistics, but I have not seen it done. Okay, find a single Metropolis Hastings algorithm in the conventional sense where you can prove a contractivity estimate in some reasonable metric. Okay, so we know from this I could probably prove it in one of these V-weighted metrics, but I would not get good constants. Do it for random orth Metropolis on something strongly log concave, and I will be extremely impressed. Yeah, more applications to sort of particle methods. People are using particle methods in more interesting ways these days, I think. And this theory is pretty well adapted to some of that stuff, particularly with the work that Ebele and people have been putting in. Yeah, contractivity for tempering stuff I touched on briefly earlier. And of course, one which will be close to the heart of many people in this room would be piecewise deterministic Markov processes, which have painfully non-contractive dynamics, I would say. So they sort of move in straight lines at a constant velocity. And so you have to do something clever for sure. That'd be good. And so yeah, there's a lot to be done. And hopefully this has been interesting. And I'll sort of wrap up there. So thank you.
Do you have any questions?
So I had an open problem which I wanted to give to Lionel, which was, so I just think this might be interesting to say. So, right, so for this stuff that Ebele does here, the main application is to, he actually studies sort of Langevin type things here, right? So it's for well adapted to things where you have strongly convex potentials in the tails and then a bit of fluctuation in the middle. And then he has another paper where they do something similar for underdamped Langevin, but they have to change the assumptions, actually. They add in a Lyapunov condition and stuff like this. And I think it shouldn't be needed. I think probably with the same assumptions, you should be able to prove something for underdamped Langevin. And I would be thrilled to see that. And in a way, that would be even more interesting, because I think people some people act as if underdamped Langevin should be particularly robust to non-convexity and stuff like this. I don't know whether that's true, but I think the results should exist, and I would really like to see that. So this one is in PTRF, and it's called, reflection couplings for diffusions or something like this. He has the one with Gilan and Zimmer, which is, I think, quite a long one in transactions of the AMS or something. And then there's one with the same set of authors, but also Alain Domus, and that's a really short one. Yeah, but he's done many things on couplings in the last 10, 15 years for sure. There's a lot of stuff on HMC that he's done with Nawaf Bourabi that I haven't really touched upon. But again, it's like, you would struggle to find two people in the world more comfortable with a reflection coupling at this stage. And so they've sort of pushed it pretty far. One thing I didn't emphasize so much, because the examples are much more technical to get into, but one thing that's very interesting is when you're working with anything that has the flavor of a particle system, whether it's a graphical model or interacting diffusions or something like this, these L1 type metrics are absolutely crucial. Many of the results will not hold for standard metrics, and you really need to acknowledge that it's a particle system somehow. Of course, when you have enough convexity, everything goes through, but that's sort of not so informative mathematically, I think.
Is that again what L1 and particle systems? So why is it? Or...
So for yeah, so in the so in these sort of papers here, like the Domus et al. One, they're working.
What is it? Is propagation of chaos?
What is propagation of chaos? Or?
No, but that's about propagation.
Sure, but the proof techniques they're using would definitely give you just direct convergence already. I think it's probably in Andreas's other paper. Okay. But it's basically, when you're coupling it, it's like you have one system of n particles and another system of n particles, and there's non-convexity all over the place. And so you sort of have to do a coordinate-wise transformed metric, where you do something like the sum over the particles f of d xi yi, something like that. And if you did the f on the outside, the argument would not work. Or if you did some L2 type stuff, it's not obvious that it would work either way. But somehow it's like, it's hard to say this rigorously somehow. But if you were trying to get sort of LP type convergences of the distance, often that's more demanding and sort of L1 type convergence is the least you can reasonably ask for. It's like the easiest one to make contract under these non-convexity conditions. But I don't really have a good explanation for why that's the case. But from the papers I've read, it seems to be crucial to work with L1 type stuff for particle systems.
So if you go back to what you said in the beginning, I mean, maybe the first slide or something like this, right? You had a metric space, and why did I choose the metric space to be already probability distributions, right? For example, related to interactive particles, the particle system. Look at probability measures on measures, right? So I could still abstractly write this, right? And then I could still maybe define the sculpture and and has this been?
I don't know. I think the closest would be there will be some forms of McKean-Vlasov systems where the analysis looks a bit like this, but nothing much more abstract than that, I think.
All right.
Cool.
Then we can stop recording. Are you happy to share the slides?
Yeah.
Okay, then I will send you an email with the slides. Super useful. And now we can go upstairs and there are pizzas on the common room. Yeah, there is